Hello everyone, and welcome to the video for section 11.5, area under the curve. In this video we are going to be looking at ways to go through and calculate and estimate the area under the curve, and eventually we'll show you a method that we can use using limits to actually find the area under the curve, the exact area. So to get started on this one, our skill objectives are first, to find limits of summations. So we're going to be looking back at the whole series, and we're going to be taking the limit as n goes to infinity there. Find the area under a curve and using rectangles, so we'll approximate the area using rectangles. And number 3, actually finding area under a curve using limits of summations. The conceptual objective on this one is understanding that when we use rectangles to approximate the area under a curve, the more rectangles we have, the better the approximation is going to be. Okay, so as we're working on these problems, what we're really going to be doing is we're going to be looking at calculating, approximating the area in this region that's going to be bounded by a curve y equals f of x, the x-axis, and x equals a and x equals b. So we're going to have this region. And to go through, the way we go about working on this one, we will go and we will break our region up into sections where the base, the width of each section is going to be the same, or try to have that be the same. It doesn't necessarily have to be, but a lot of times when we're working on these things, the ones we're going to work with, we'll want to keep that the same. So we'll go through, break this up. Let's pretend I've broken this up where we're looking at the base here. The distance from here to here is equal across all these places. And what we can do here, we can go and approximate this. What we're going to do is use rectangles. And when we work with these, the base that we use is this length, whatever the change in x is here. That's where our goal is that will always be the same. So this will be delta x. And then the height of our rectangle is going to be used by picking a value to be a sample point, and we'll plug that sample point into our function to calculate the height. Typically what we're going to use is either the left endpoint or the right endpoint. So if we are going to use the left endpoint, what I'm going to do then is I'm going to go through for each subinterval. So for this subinterval, I'm going to use this value there. I'm going to plug it in, and when I go through and draw across here, that will represent, this will be the rectangle I'm going to find the area of. And then I can add that up. I'll go through and find the area using the left-hand endpoint of each subinterval to calculate the height. And then I can go through, again, I can take each area and I can add those, in this case, 4 rectangles, and I will get an approximation for the area between my curve and the x-axis from x equals a to x equals b. Please note that I do have, in this case, I do have error. I have an underestimate here. I have a little bit of an overestimate, but you can see that probably in this case, our approximation is going to be an underestimate. And one of the ways we can improve this is by going through and increasing the number of rectangles. So in this case, I had 4 rectangles. If I cut, let's say I want double the number of rectangles, then all of a sudden it's going to decrease the error that we have in there. The more rectangles I have, that better that approximation is going to be. Okay, so what we're going to be working on, what I hope you recognize from the previous diagram, was that when we're working on these things, really what we're doing is we're taking summations. We're adding areas of rectangles, which is a summation. It is a base times a height. And so we're going to be able to go through and eventually go through and write the area of a rectangle underneath a curve in terms of a base times height. But to start out with, to work with these things, we're going to be dealing with some summations. And we're going to need to be able to simplify them and evaluate them. And so to do that, we have some properties. The properties we have here, first up, when we have the sum as k goes from 1 to n of a constant times the terms of the sequence a sub k, we can pull that constant out. It's just going to be the constant times the sum of the sequence, the series. Then these two are kind of the same. If you notice, the only difference between them is the plus and the minus there, and that's why you're only going to see the difference here, plus and minus. And it's really the idea that if I'm going to take a sum as k goes from 1 to n of a sub k plus b sub k, two general terms, I can just find the sum of each series individually and add those results together. And the same thing with the difference. I can find the sum as k goes from 1 to n of a sub k, find the sum as k goes from 1 to n of b sub k, and just subtract those two results, and that will give me this difference, what the difference between the sum as k goes from 1 to n of a sub k minus b sub k. Now, to help us evaluate these, we're going to look at these formulas that we have. Now, really what we're dealing with here are, except for the first one, everything is going to be a power on k, and you're going to see it's k to the first, k to the second, k to the third. The other thing you have to keep in mind, we can find a similar formula for things like k to the fourth, fifth, sixth, and so forth, but for our purposes, we just need to worry about these right here. The first one, the sum as k goes from 1 to n of a constant is just going to be the constant times n. For example, if I said the sum as k goes from 1 to 10 of 5, that would just be 5 times 50, or 5 times 10, which would equal 50. The other ones you have are these formulas, and that's really going to write that sum, this sum, as really a polynomial, if you will, in terms of n. So the sum as k goes from 1 to n of k is going to be n times n plus 1 over 2. The sum as k goes from 1 to n of k squared is going to be n times n plus 1 times 2n plus 1 over 6. And the sum as k goes from 1 to n of k cubed is going to be n squared times n plus 1 squared divided by 4. So literally what's going to happen here, if I just put, let's say I want to know this, if I wanted n to be 10, like I was looking at the sum as k goes from 1 to 10, I could literally put 10 in for any of these n's and then evaluate it. Let's take a look at a couple examples. First, let's take a look at this problem here where we're asked to evaluate this sum as k goes from 1 to 10 of 3k squared. Now, we could go through and just plug in 1, 2, 3, 4, generate the 10 terms and add them up, but really what we want to do is get used to using the formulas. So, on this problem, one thing you need to remember on this one is we know that the sum as k equals 1 to n of k squared is equal to n times n plus 1 times 2n plus 1 over 6. So in this case, I know n is equal to 10, so this is going to be 3 times that sum, n times n plus 1 times 2n plus 1 over 6. But this time what we're going to do is we're going to let n equal 10. So on this, I'll say, well, 3 does go into 6 twice. So this whole thing is going to be 10 times, I'll put 10 in for n, 10 times 11 times 21 all over 2. And then it's just a matter of multiplying that out. So when I go through and calculate that, I'll have 2 goes into 10 5 times. So I have 55 times 21, and when I have calculate that, that will come out to be 1,155. So this summation right there is equal to 1,155. Now let's take a look, though, at our next problem. In our next problem, we're dealing with this sum. Now notice I'm not going through and putting a value for n in. So what I'm really going to end up with here is my final answer is going to be similar to what I had right here. So on this problem right now, the first thing I want you to notice is that I'm going to start by rewriting. And notice I took, this is 2k minus 5 over n squared. I pulled the 1 over n squared outside because really our variable in this problem is k. It's not n. N is being pulled out. So that's why I could pull that outside. And so this is now equal to 1 over n squared times the sum as k goes from 1 to n of 2k minus 5 is going to be 2 times the sum as k equals 1 to n of k minus the sum as k equals 1 to n of 5. So now on this problem, I can now go and use my formulas. I have a formula for this portion right there. I know that is going to equal, in this case, that's going to end up equaling 1 over n squared times 2 times this portion right there is going to be n times n plus 1 over 2. And then we're going to go and subtract. Now, I again have a formula for this. This is a constant, so it's just going to be minus 5 times n. And then when I distribute, in this case, the 2 will drop out there. And when I distribute the 1 over n squared, I'm going to get that this sum is equal to n times n plus 1 over n squared minus 5n over n squared. Or I can just say it's n times n plus 1 over n squared minus 5 over n. And that would be my final answer on this. It's going to be an expression in terms of n. What I'd like you to do right now, pause the video, make sure you're comfortable with all the different calculations, especially remembering these formulas, where those formulas, if you don't remember them, look back in your notes and look them up, make sure that they are correct and you understand how I applied them and used them. And once you're done, we'll move forward. So once we've gotten that expression in terms of n, the next thing we want to do is take the limit as n goes to infinity. And really what we're going to be looking at here is we're going to go back to the horizontal asymptotes. Again, back to what we dealt with back in chapter 2. And if you remember, we could do that by inspection. We looked at the degree of the numerator, degree of the denominator. And if they were the same, that's when you got a numerical value. And it would be just the ratio of the leading coefficients. Now, the one thing you're going to have to remember on this, you're going to have to look, even though, because if you take a look on this, the denominator here is 2. So this is second degree, but this is also second degree, even though you gotta think about what would end up happening if you multiplied it out. So in this case, I would end up with an n squared. So what we're really doing is taking a look at the problem we just did, and we're going to take the limit as n goes to infinity. So if you remember, what we just did is we just showed that this sum right here is equal to this expression right there. And now I'm going to take the limit as n goes to infinity. Well, in this numerator, this is going to be, and if I was to distribute the n, I'd have an n squared plus n over n squared. The leading coefficient in both cases is 1, so it's 1n squared there and 1n squared there. And since the degree of the top and bottom is the same, it's just going to be the ratio of the leading coefficients, which would be 1 over 1 or 1. The limit, and then we just subtract the limit as n goes to infinity of 5 over n. Because our variable is in a denominator like this would end up being 5 over infinity, which really I just want you to think of as 0. So this limit here is going to become 1 minus 0, or just 1. Now let's take a look at a different problem. Now this one right here, we're going to take the limit as n goes to infinity. Let's go through the whole expansion process. So it's going to be equal to this. We want this limit as sum goes from k goes from 1 to n of this minus that. So the first thing I'm going to do, I'm going to take everything that's not k. In each case, I want to think of this as the sum of this by that third property. It's going to be the sum of this minus the sum of all this. And I'm going to pull out in each case, what you'll notice what I did from going from here to here is I rewrote it as, and separated it with the sums, but I also took everything that's not k and pulled it out. So this was a 2k cubed over 3n to the fourth. So I wrote that as I took the 2 and 3n to the fourth outside, and so I just have the sum of k cubed. Minus, in this case, 7 over 4n squared. I pulled that out as the sum of k. And then it's just a matter of remembering the formulas. I know that the sum as k goes from 1 to n of k cubed is n squared times n plus 1 squared over 4. And the sum as k goes from 1 to n of k is going to be n times n plus 1 over 2. Now when I now multiply this out, so I took the 2 over 3n to the fourth times this, I will get 12n squared times n plus 1 squared over 2n squared times n plus 1 squared over 12n to the fourth minus 7 times n plus 1 over 8n squared. Now here's the key part on this. At this point now, we are able to go and reduce. I'm going to start, I'll take this, I'll reduce that out, make that a 6. But also I want you to recognize that this is an n squared there, and if I was to FOIL out this portion right there, I'd also get an n squared. So the degree of my top and bottom of the top here would end up being, if I multiplied it out, would come out to be n to the fourth. So therefore, we have the same degree, so the limit as n goes to infinity is just going to be the ratio of the leading coefficients, which in this case for that portion is 1/6. On this second piece, again, if I multiplied it out, I'll have an n squared and an n squared there. So the ratio, that limit as n goes to infinity, is also going to be just the ratio of the leading coefficients, which is going to be 7/8. So if I want to go through and actually evaluate this, I have to get that common denominator. So this would end up being 1/6. The least common denominator would be 24. So that would be 4 over 24 minus 21 over 24. So this whole expression right there, that limit as n goes to infinity of that piece, will come out to be negative 17 over 24. That would be my final answer on that one. Again, at this point, I want you to pause the video, take a look at what I've done to go and do these calculations, make sure you're comfortable with it, and once you're done, come back, we'll move forward from there. Okay, now looking at the area problem, really what's going to end up happening, and we kind of already talked about this, but I want to just show it again, is we're going to be given a function y equals f of x, and we're going to go and graph this out. And we're going to be asked to find the area of a region that's bounded by our function, the x-axis, and two vertical lines, in this case, x equals 0 and x equals 5. And when you're asked to do this, what you're really going to be doing initially, the first one, is they're going to tell you, oh, we want you to go through and do this, and we want you to go and they'll tell you how many rectangles you want to use. So in this case, let's say they wanted us to use 5 rectangles. And so I'm going to break this up into 5 strips of equal width. So in this case, I'm going from the change in x. If I want to know what delta x is, which is the change in x, I know delta x in this case, if I want to use 5 rectangles, it's going to be this total distance there, which is 5. And I can find that by taking 5 minus 0. So I'm going from 0 to 5 all over the number of rectangles. So in this case, I know I'm going to go through, and every 1 unit, my base of my rectangle is going to end up being 1. So what I'm going to do then is I'm going to go and draw in the rectangles. So I have those lines, and those represent the left. We have the left and the right endpoint for side of each rectangle. Now the other thing that's going to happen is they're going to ask you to go and do either a left hand or a right hand endpoint sum. So what that means is this: if I'm going to use a left hand sum, okay, that means I'm going to go for each to go through and draw in when I draw in the rectangles, I am going to go and start from the left hand endpoint. That is going to represent the height of the rectangle. So I will end up, in this case, if I was doing a left hand sum, I would take there. In this case, since this one is, when I'm up over here, this is higher than that. So it's going to be, I'm going to be an overestimate there. Same thing here. But over here, my left-hand endpoint is below the other one. And that's what's going to end up happening over here as well. And finally there. And I could then calculate, take that area and add up each one of those. So if I could sit there and say, there's area 1, area 2, area 3, area 4, area 5, I can go say it. I can say the area, that area is about equal to my values for A1 plus A2 plus A3 plus A4 plus A5. I could just add those 5 areas up, and that would give me a good, a decent approximation for the area between the curve and the x-axis. Now keep in mind, I can choose to do, instead of a left-hand approximation, I can use a right-hand approximation. So if I did that, then I'm going to go through and I'll end up using the ones that I'm going to have with the purple here. I would end up going through, and with my right hand, I would come here, 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 there, and there. So that would be what you see with the purple would end up being a right-hand approximation. And again, I can then go through and take the areas that I have that I calculated using the purple. So I'd have, again, instead of the red A1, I'd take each one of those areas and add them up, and that would give me another approximation. The end result is, what I want you to recognize is that the area, an area of a rectangle, is going to be equal to the function's value at some particular x value, call it x sub k, times, that's going to be the height of the rectangle, times delta x, which represents the length of the base. So every rectangle is going to be, I'm going to plug some x value, either the left-hand or right-hand endpoint of the subinterval into the function. I'll evaluate the function at that x value. That value will be the height of the rectangle multiplied by delta x. And so when I find these, in this case, I would have an expression, and I know I would just be taking the sum with, I have 5 rectangles, as k equals 1 to 5 of f of x sub k times delta x. And that area would be approximately equal to that sum. Okay, let's take a look at an example. So in this situation here, I am going to go through, I'm going to let f of x equal x squared plus 1, and I want to find an approximation of this region right here on the interval from 0 to 2. I want to approximate that area using 4 rectangles. So the first thing I need to do with this is I need to go and calculate delta x. So delta x in this case is going to be 2 minus 0, because that whole length it's going from 0 to 2, so 2 minus 0, and it's the number of rectangles is 4. So delta x is going to be 2 over 4, or 1/2. So I know I'm going to go through, when I make my rectangles, I'm going to go about halfway between. Okay, now, so I draw in my strips for 1/2, and here we go. Now, the only other thing I have to know is they didn't specify it here, but they will in the book. They're going to tell you which type of sum they want you to use. So let's start out. We'll approximate this using a right-hand sum. So in this case, since I'm using a right-hand sum, I am going to go and to get the height of my first rectangle. So I'm going to, if I draw that in, it's going to come across there, my right-hand sum. There's the rectangles I'm going to be working with. And so area 1, to calculate the height, I know that first area is going to be, I'm going to plug in 1/2 into x squared plus 1. So that I know the height is going to be 1/2 squared plus 1. That's going to be the height of that. Multiply it by my base, which is 1/2. So 1/2 squared is 1/4, plus 1 is 5/4, times 1/2 will come out to be 5/8. Take a minute, double check that calculation. I'm going to have to do that for each one. Okay, so for area 2, my sample point now is what's going to give me the height is when I plug in 1. So the height of my rectangle is I'm going to plug my sample point 1 in for x, so it's going to be 1 squared plus 1 times my base. The base of the rectangle is always 1/2 in this case because that's what delta x was. So now that will end up being, when I multiply that out, I'll have 1 squared plus 1 is 2. So that will end up being equal to 2 times 1/2, which is 1. Now, but I'm going to write that with so I already have my common denominator, which in this case will be 8/8. What I want you to do right now is I want you to pause the video. I want you to calculate your area 3 and area 4. So once you have those, come back and we'll take a look at your calculations, and then we'll finish this problem up. Okay, welcome back. You should have gotten, when you did this for area 3, I came up with 13/8, and for area 4, I came up with 20/8. So double check, make sure you got double check your calculations if you didn't get those. And what we're now going to do, once you're comfortable with that, we'll go through and we're going to go through to calculate our approximation on there. I'm just going to add those up. So I'm going to take 5 plus 8. So I'm going to take the 5/8 plus 8/8 plus 13/8 plus 20/8. I'll add that up. So 5 plus 8 is 13, 26. So the result there is going to be 46/8. Or if I reduce that, that's 23/4. So that is going to be my approximate area between the x-axis and f of x equals x squared plus 1 from 0 to 2. Again, notice that if I went through, I increased the number of rectangles, I'm going to get a better approximation because I'm going to decrease the error that I have here. Also, I want you to notice here in this particular one, because it's a right-hand sum and our function on the interval was always increasing, I know that this right here is an overestimate of that true value. Okay. At this point, again, pause the video, make sure you're comfortable with all the calculations, and once you are, we'll move forward. Now what we're going to do is really go through and try to use everything we've done so far in this video. We're going to use that. We're going to come up with a way to use that to go and actually calculate what the exact value of that area is. So our definition here is where f of x is a continuous non-negative function on the interval from a to b. Now, this is going to be, when we're setting this up, we're always going to, it's in general A to B. A lot of the problems that we have in the book, that's always A is going to end up being 0. And that's going to be actually a good thing. You'll see that why in a second. The area of the region bounded by the graph of f of x, the x-axis, and the vertical lines x equals a and x equals b is given by a equals, that area equals the limit as n goes to infinity of the sum as k goes from 1 to n of f of x sub k times delta x. Now, again, you need to remember here that this portion right here, that's the area of a rectangle. The base of the rectangle is delta x. That's equal to the base. And the base is going to be, the width of that is going to be the width of the rectangle. And so the thing to remember here is delta x is always equal to the right-hand endpoint minus the left-hand endpoint divided by n. So whatever b minus a over n, that is going to end up being the value of the base. That's going to be what we're going to be multiplying by. Now, in general, I can use either left hand or right hand. Our life is going to be easier a lot of times to use a right hand endpoint. So therefore, what I want you to do is just remember the right hand endpoint. So remember when we were going through and on that previous example, we used the right-hand endpoint, so we plugged in, for the first rectangle, we plugged in 1/2, then we plugged in 1, then we put 3 over 2 in, and then 2 finally into the function to generate the final height. So our right-hand values are always going to be whatever A is, whatever we're starting with, plus k times delta x. So our right hand, when we did when we were looking at that last example, we were going from 0 to 2 using 4 rectangles. So I know delta x was 1/2. So the value I plugged in, I took 0 plus k was 1 times 1/2. And that gave me the 1/2 that I would plug into the function. And then when the second one, it was 0 plus, and for the second one, k is 2 times 1/2. So that gave me the 1 that I plugged in. And so forth. I can just keep doing that to generate. But in general, this is what you're going to use. Okay, that is always going to be, that's going to be the sample point. And so the height of our rectangle, that the rectangle that we're going to be working with, is always going to be the function's value at x sub k. So in this case, it's going to be f of a plus k times delta x. That's the value that's going in. Now, the key thing here on this is to remember a couple things. Number one, right now this is probably looking a little bit more confusing because of the letters. We'll actually be looking at that problem we just did using numbers in a little bit. So you just want to be careful with that. The other thing is, again, on a lot of the problems that you're going to notice, that you're going to see, that in at least what we're working with right now, A is going to be 0. We're going to be looking at the interval where we're on an interval from 0 to something. That won't always be the case. And as you move forward, you can kind of, into other classes, you can expect that value won't always be 0. But for right now, most of the time, it will end up being 0. I might, as a challenge or an extra credit, I might throw a different value for A, but for the most part, when I give you a problem to do, A will be 0. So now let's take a look at the problem that we were just working on, where we're taking a look at, we want to actually find that exact area. So the first thing I need to do in this one, and I went through and did already, is I have to find delta x. Well, because I'm using n rectangles, delta x is going to be 2 minus 0 over n, which will be 2 over n. And since we're going from 0 to 2, my sample points, x sub k, is going to be at 0 plus k times 2 over n, which will be 2kn. So notice, this is the value I'm going to plug in for the variable so I can generate the height. So in general, I'm going to take that 2kn, I'm going to put it in for x. So f of x sub k is going to be 2kn, that thing squared, plus 1. And when I multiply it out, this is what I get. So the height of my rectangles, the kth rectangle is going to be this. And so what this means is this is the height, this is the base. To get the actual area of the rectangle, I'm going to multiply my base and my height. And I'm going to add those up. So the area, by our definition, is going to be the limit as n goes to infinity of the sum from k going from 1 to n of my height, 4k squared over n squared, plus 1 times 2 over n. And the next thing I'm going to do, I'm going to go and distribute the 2 over n inside. So that's going to equal the limit as n goes to infinity of the sum as k goes from 1 to n of 8k squared over n cubed plus 2 over n. Now remember what we did before when we were going through and evaluating these limits. The first thing I'm going to do is I'm going to take everything that's not involving k, I'm going to pull it out away outside of the summation. So this expression here will become this. I'll take the 8 over n cubed, pull that out. I'll pull out a 1 over n, and so I get this. And at this point, we have to go back, and you still have to remember your formulas. The sum as k goes from 1 to n of k squared is going to be n times n plus 1 times 2n plus 1 over 6. So this portion right here is equal to 8 over n cubed times n plus 1 times 2n plus 1 over 6. This part right here, the sum as k goes from 1 to n of 2 is just going to be 2 times n. So this portion right there will come out to be 1 over n times 2n. Now, we're taking the limit as n goes to infinity. So the first thing, and I skipped some steps here, but when you look at this piece right here, the first thing I want you to notice is if I multiply these three things out, that's going to end up being a 2n cubed. If I multiply that by 8, it's going to be a 16n cubed. And when I multiply these two together, I have an n cubed there. So my leading coefficients in this case, in the numerator, would end up being 8 times 2, which is 16, over 6. So the limit of this piece right here, if I was to multiply everything out, I'd have a third degree polynomial on top, a third degree polynomial on the bottom, and the leading coefficient in the numerator would be 16. The leading coefficient in the denominator would be 6. So that limit as n goes to infinity will be 16 over 6. This one, the n's actually will go and cancel each other out. So this piece right there is just going to be 2. So I get 16 over 6 plus 2. If I get the common denominator, 16 over 6 plus 12 over 6, that gives me the 28 over 6. And 28 over 6 reduces to 14 over 3. So take a look. I want you to pause the video. And I want you to make sure, I want you to look at that, make sure that you're comfortable with that. You won't have a lot that you're going to have to do like this, but I will ask you in the homework to do a couple. Okay? So again, the key part on this, in each one, when you have something like this, find delta x, find what x sub k is, plug x sub k into your function, into the variable, and simplify. And just remember, at that point, your base is here, your height is here, and you can write your summation right at that point. And that's just a matter of finding that limit as n goes to infinity. So with that, I hope everything is going well. We will make sure you're comfortable with these and take as much notes as you have. Indicate any questions you have. I do anticipate that there will be some questions dealing with especially this last part. But with that, I hope things are going well and you're having a good evening, and we'll see you in our next class.